So we have two speakers here to talk about our conclusions with respect to developed country markets where there is a transition going on from conventional energy sources to renewables that will be largely paced by the economics of decommissioning, in many cases, perfectly good assets in favor of lower carbon assets. And in developing countries where there's a rapid growth in new energy generation as a result of economic expansion, um, that's different, and that has an effect on the viability and suitability of different storage technologies. So let me bring our next two speakers in. First is Kathy Wang, who is a former PhD student at MIT and is now at the International Electricity Vertical, Enel. Welcome, Kathy. And my current Mighty colleague, Derek Malapragada, who's another senior leader of Mighty's systems modeling group. Welcome, Derek. And I know that Derek's wife is expecting to have a baby at any time now, so I'm hoping we get through this hour without any mishaps. And I'll take a risk by asking Kathy to go first and hope that Derek survives for another 20 minutes. Kathy.
All right, thanks, Rob. I'll just make a slight correction. I was a master's candidate, not a PhD
Oh, fair
level.
enough. Okay, good.
I was in the technology and policy program. But good morning, everyone. My name is Kathy, and as Rob said, I was a research assistant working on the future of energy storage study. I was specifically on the modeling team, so I just wanted to give a quick shout out to all of the contributing authors for Chapter 6. So chapter 6 really is focusing on the role of grid scale storage in developed countries such as the US, which has relatively high levels of grid reliability, universal access to electricity, and increases in electricity demands that is driven by the electrification of different end use sectors. So before I jump into the findings, I really wanted to focus on how the electricity grid that we're modeling in the year 2050 is very different from the one that we have today. And that is because the share of VRE generation is expected to grow. Many businesses, governments are looking at net zero carbon economies. So what does that mean exactly? Looking at the table to the left, we can see that the US total grid emission intensity for 2018 was 449 grams of CO2 per kilowatt hour. So driving that down to zero will mean even more reduction on the tonnage of emission side, because we're going to be expecting a lot of increase in overall demand. So even though the US has experienced significant emissions between 2005 to 2018, much of that remains to be done in terms of getting to a near zero carbon future. Which brings me to the second point of how will electrification of other sectors affect electricity load. And you can see in the difference between the two charts on the right that demand increases in light duty vehicles, as well as commercial and residential space heating, will really increase the electricity load that we can expect to see in 2050, where the overall load is higher, but we also see higher peaks. So all of these contribute to the topic that we're going to be discussing today, which is the large scale integration of wind and solar through the design of flexible power systems that can balance the variation in wind and solar output. So the modeling of these non-dispatchable energy supply and demand flexibility really require complex modeling to take into account these intertemporal complexities. And the model that we use is GenX, which is open source. You can give it a try at this link right here. And GenX really takes on the perspective of a cost minimizing central planner to determine the optimal generation, storage, and transmission investments mix that are needed to meet this predefined system demand while adhering to different operational constraints. And so like other state-of-the-art capacity expansion models, GenX has the capability of modeling operational detail of thermal fleets. So, I mean, up and down, oops, sorry, going back here, of up and down ramping rates, as well as different ramping times. And it is also able to do very highly resoluted temporal resolutions, and we do that on an hourly basis for both demand and our VRE capacity factors. We are able to model both demand side and supply side resources, and are able to expand upon the existing transmission network by using this configurable network and market representation. So we explored the role for storage and power systems for 3 key regions in the US. The US Northeast, which is made up of New York and ISO New England regions, US Southeast, and Texas. And we have selected these 3 regions because they are all have very different starting points in terms of their grid emissions, but also because of different policy and resource availability criteria. So in the Northeast, most states have pledged to reduce their emissions by at least 80% by 2050. And due to the electrification of heating, it is likely to go from a summer peaking system to a winter peaking one. There are well-documented siting difficulties for both onshore VRE and transmission developments, as well as the availability of low carbon hydropower from Canada. The US Southeast is characterized by being made up of different vertically integrated utilities, and there is significant nuclear fleet, which contributed 28% of the region's power generation in 2018. So nuclear is most likely to be given a second license renewal, making them still available for use past 2050. And finally, Texas is a region with little transmission to the outside, but with very high quality VRE resources, as well as high industrial demand, which increases its potential for using demand flexibility. So to assess the role and applications of storage, we evaluated these 3 regions under a range of technology and policy assumptions. So I list some of them below. You can see that we have evaluated different emission constraints ranging from 50 to 5 grams of CO2 per kilowatt hour. And for reference, compared to the 2018 level, this is about 97 to 99% decarbonization. So very much near zero carbon. We also use the NREL electricity future studies projection of the substantial increases in electricity demand that is consistent with a highly electrified economy. And we use the NREL ATV's cost reductions for VRE and lithium ion storage by 2050. We assume sparing use of natural gas generation with CCS technology. And given that most of the existing fossil fuel generating plants will have retired by 2050, we assume mostly greenfield conditions for evaluating these systems, with the exception of hydropower from Canada in the Northeast and some existing nuclear capacity in the Southeast. So here are the first sets of results where we're considering using today's commercially available technologies. So utility scale solar, wind, natural gas plus CCS, and lithium ion battery storage as the only available storage technology. Here we see that near complete decarbonization of the electricity system is feasible from an hourly energy supply and demand balance perspective, which is quite encouraging, using renewables, natural gas, and lithium ion only. We evaluate different emissions constraints. So the no limit, so that means no constraints, serves as a benchmark for assessing the impacts of imposing incremental emission constraints. And we see that as emission limits tighten, natural gas is incrementally replaced by VER and lithium-ion buildouts as expected, as well as gas and CCS capacity, mainly in the 5 grams of CO2 per kilowatt hour case. This overbuilding of VRE really allows for a relatively short duration requirement for lithium-ion battery on a scale of 2 to 4 hours of mean system load. But the challenges of getting to this sort of net zero system vary across the regions based on their resource endowments and demand patterns. And we can really see this in the differences in the system cost of energy, which is defined as the total annualized investment and operational cost of the modeled system divided by the total annual electricity demand served. So we see that the Northeast is relatively more expensive than Texas to decarbonize. And that is because of the factors that I raised earlier. It's more expensive due to siting constraints for onshore VRE, transmission, and has lower quality VRE resources. And this is compared to Texas, where it has much higher levels of VRE deployment, even at the no limit case. And this is because Texas has higher quality VRE resources. So this really illustrates the challenges that system planners are faced with, which is that they need to take into account these differences across regions in order to make tailored plans for decarbonization. The next set of results reflects the impacts of emerging LDES technologies. So I think this is a summary slide of what was discussed earlier in the session, where we have electrochemical, mechanical, thermal, and chemical storage types. But our experimental design is really aimed at understanding the relative merits of different classes of storage, not necessarily picking a winner. So rather than evaluating all of these different technologies, we classify them into 3 main classes based on 3 key design attributes, which are discharge capacity cost, storage cost, which is $1 per kilowatt hour figure, and round trip efficiency. So in brown, that's what I would define class 1. These are mainly the lithium-ion batteries, which are characterized by their high storage cost, low discharge cost, and high round trip efficiency. Class 2, which are mainly composed of redox flow batteries, are characterized by middle of the pack storage costs, discharge costs, and round trip efficiency. And then finally, class 3 technologies, which are made up of hydrogen metal air batteries and thermal storage technologies, which have very low storage costs, but high discharge costs and low round trip efficiency. So the model, the way we characterize these different or parameterize these different technologies is through a bunch of variables, including all of these, the 3 characteristics that I have highlighted, as well as the charging capacity costs, the fixed O&M, variable O&M, and the efficiencies associated with discharge and charging. So let's take a look at the impacts. Here, looking at the legend, it goes from base case, which is lithium ion only, class 1 storage technology. And then the next one is plus the class 2 storage technology, which is redox flow batteries. And then the next 3 are the impacts of adding 1 of the class 3 storage technologies. So again, we're not picking a winner, we're just evaluating what is the range of impacts of operating these 3 classes of storage technologies. So first, we see that LDES really substitutes for natural gas capacity. It increases the value of the variable renewable generation by reducing the curtailment of VRE and decreases electricity price volatility, which will be covered in tomorrow's session on regulatory frameworks. A question that we get asked a lot is, what does long duration energy mean? What types of durations are we seeing? And from this model, we see that the storage duration for long LDES resources range from 39 to 59 hours, So not as long as the weekly and seasonal sort of durations that many folks are talking about, but rather on the scale of days. So this is compared to lithium ion storage duration of 1 to 2 hours. Next, looking at cost, we can see that as long as some emissions are allowed, it is optimal to have gas and CCS capacity. These have very low capacity factors on the order of 2 to 5%, but they're important in these sort of long periods of system stress where we have continuous days of low wind, for example. Thus, the cost impacts of LDS are greatest when natural gas generation is not an option, i.e. at the 0 grams per CO2 per kilowatt hour scenario. But again, it is too early to pick a winner among these emerging LDS, and we recommend that more R&D is put into all of these different classes in order to have a more wide-scale, commercially available technology to be used before 2050. This, I think, is a fairly understated point, which is that storage operations are complex and do not follow simple cycling patterns. I think the typical wisdom is that when it is cost optimal to deploy technologies with the lowest cost of storage, these are generally best suited to provide long-term storage, and we can see that in the graph to the at the top, where for the 10 grams of CO2 case, we see that lithium ion is mainly doing daily cycles versus hydrogen, which is more doing monthly cycles. So I think that's the general wisdom. But we see that optimal storage operation is very different from optimal generation dispatch, and it does not follow the rule of the least marginal cost. And this is because there is the shadow value of stored energy is changing, and it varies as a function of the grid conditions at the time of charging and discharge. And so as a result, all of these storage technologies deploy will operate with charge and discharge cycles of various durations. And we can really see this in the frequency analysis shown in the table. And this is the frequency analysis of the optimal state of charge of different storage technologies. We can see that at the 10 grams of CO2 case, as expected, lithium ion is providing daily cycles, whereas hydrogen is providing monthly cycles. But as the emissions constraints tighten to 1 grams of CO2 per kilowatt hour, both of these storage technologies are providing seasonal cycling patterns. So this is really indicative that simplified assessments of storage economics based on stylized charge and discharge profiles really overlook these dynamics and provide inaccurate assessments of storage value. This is why a system study is needed, and more sophisticated and analytical tools are needed to plan, operate, and regulate the power systems of the future to ensure that these are cost efficient, but also reliable. That brings me to the third sets of results, which are the different substitutes for storage. The first substitute that we can think about is intraday demand flexibility, and that's flexibility coming from applications like EV charging that is typically competing with short duration storage. On the graph to the left, we see that the scenario with demand flexibility has reduced need for lithium ion storage, both on a capacity and on a power and energy capacity basis. And when we see this in operations, we see that lithium ion batteries discharge and charge cycles become less frequent if you focus on the areas colored in brown. So I think that is fairly straightforward, but demand flexibility at a large scale can also serve as a substitute for the need for energy storage. And as Emre alluded a few moments ago, here is an expanded role for hydrogen for use in other sectors beyond use just in the power sector. And so under this sort of framework, we can assume that a portion of industrial hydrogen demand is met by electricity. So these are what the 25 to 100% indicate, with 100% corresponding to 19.7 gigawatt hours of hydrogen demand in Texas. And within this framework, storage can provide hydrogen either for industry, so going from grid electricity, electrolysis to hydrogen demand for industry, or it can serve electric load, which goes from electrolysis to storage to H2 back to power. And so, in other words, hydrogen for industry and heavy duty transportation can be produced either directly through electricity from the grid or through electricity from storage. And we can see that this sort of flexible production of hydrogen for other sectors can improve asset utilization, as you can see in the electrolyzer capacity factor chart. You see that as we use or substitute more of the hydrogen production using electricity, we're increasing the utilization of electrolyzer. Same goes for the hydrogen storage component. We reduce VRE curtailments and reduce the cost of decarbonization by reducing the system cost of energy. So I think this is a pretty important point and really signifies that hydrogen storage has sector coupling capabilities beyond just the use in power sector. I'll just drop in a quick note about the availability of low carbon dispatchable generation and how that also competes against VRE generation and lithium and storage technologies. As I said previously, we assume that in the Southeast, there is still the existing fleet of nuclear. We see that the system cost increases 6 to 15% without the availability of the existing nuclear fleet. And that capacity really substitutes for the overbuilding of VRE resources. We did test allowing the model to add new nuclear capacity, but we don't see any optimal economic deployment at the current assumed completion cost of $6,000 per kilowatt. If we were to assume lower costs and lower ultra low costs from the 2018 MIT Future of Nuclear study, we do see some deployments, but really it is competing against the very low cost of VRE generation and the reduced cost of lithium ion battery. And then finally, the final substitution for storage that we considered was transmission expansion. We know that transmission expansion plays an important role in reducing decarbonization costs and directly competes with storage. And this is very well illustrated in this analysis by Brown and Boterode, which is featured in the report, in which they show that the most connected scenario, so the one highlighted in red, deploys only 23% of the energy storage used in the isolated state scenario. And this is obviously associated with significant reductions in system cost of electricity. And this indicates that regional coordination of transmission planning has benefits. Mainly allows increased VRE deployment in regions with higher quality resources and connect them back to the load centers. And it improves VRE integration by smoothing the effects of geographical differences. But given the difficulties in siting new transmission and enabling more coordination, there is still a role for both better planning of transmission and an expanded role for energy storage. And with that, I will pass it on to my colleague, Derek, who will be explaining the impacts of storage in developing countries.
Great. Thank you, Kathy. Let me just get my screen up. So in the next few minutes, I'll basically try to summarize our analysis from the systems modeling perspective, looking at the role for storage in emerging markets. And I'd just like to acknowledge my contributing co-authors for this chapter, Mark Barbaro, who was a PhD student in electrical engineering, who led most of the work here, along with Rob and myself participating in the study. So we focused on sort of two different classes of emerging markets as being representative of, sort of the wide diversity of, system conditions that you would find in many emerging market countries. And so, we classify them as demand-driven regions, such as India, where generally power supply reliability has significantly improved and is approaching levels similar to what you would see in the US and other parts of the country, other parts of Europe. But in these regions, you're also seeing rapidly growing electricity demand, driven largely by economic development and adoption of a large number of energy-intensive appliances like air conditioning. These systems also tend to have, large shares of fossil-based generation, predominantly coal in the Indian context. But India also is uniquely sort of resourced with high-quality solar resources. So there's a lot of interest in deploying high renewables capacity over the next decade, continuing from the progress that's been made to date. So in these regions, energy storage has some unique applications related to distribution network management, but also sort of operating and planning the bulk system to integrate these higher shares of solar that are coming on the system while managing these peak load growths. In contrast to India, we also wanted to sort of look at regions where there is supply constraints. And one example region that we focused on was Nigeria, where there's well-documented power supply shortages, resulting mostly from aspects related to the availability of natural gas, but also some well-documented network issues. That means that the bulk system reliability, both from a network perspective, but also from a supply perspective, is far below what is needed to meet demand. And so there is naturally a reliance on off-grid supply sources, predominantly diesel-backed generators, but also increasingly microgrid-based applications. And so storage use cases in those networks and those systems are likely to look very different from the demand-driven example in the Indian context. So in the next few slides, I'll highlight some of our key findings from the analysis that we did for India, and then contrast that briefly towards the end to look at the situation in supply-constrained settings. So just a little bit more background about why we think India is an interesting market to study for this particular application, and in particular for thinking about energy storage adoption. So there's a number of projections around electricity demand growth in India, and one of the striking elements of these projections is that unlike in the US and other parts of Europe, where electricity demand growth is primarily expected to come from electrification of heat and primarily electrification of transportation, in India, the building sector dominates new electric demand, and much of this is coming from air conditioning adoption. So air conditioning related electricity demand not only increases your annual gigawatt hours or terawatt hours that you're consuming, but it also has a particular impact on the load shape and increases the peakiness of load. So this can be seen in the table on the right, where we're just highlighting the contribution of space cooling as projected by the International Energy Agency as part of their Future of Cooling report to India's electric demand today, but also in 2050. And you can see that there's a substantial jump in the contribution of space cooling to peak demand. And interestingly, this peak demand actually happens later in the evening post sunset. So there's also sort of a potential mismatch between the solar resource as well as when this peak demand occurs. So we already see these types of trends in hot and arid regions like the Southwest US, where generally speaking, air conditioning loads tend to be about half of peak demand, which happens during summertime. So this is not inconsistent with prevailing trends around the role that ACs can play, but the specific application of how air conditioners are adopted, the types of air conditioners that are adopted, as well as the utilization patterns, means that this could particularly be a challenge in the Indian context. So our focus of the study in trying to sort of understand the role for energy storage was very much centered around this new load growth and how that sort of interplays with system decarbonization. And so we want to really understand how AC load growth affects investments in energy storage, both at the bulk system level, but also at the distribution level. And then how that interplays with several other drivers for power system evolution, notably, renewables, availability of natural gas, etc. So to sort of study this question, we used sort of a series of analytical approaches that were developed for this analysis. Because we're sort of looking at the granular impact of load and its implications on energy storage demands, we first worked on developing a bottom-up demand characterization model that tries to sort of distinguish the business as usual load growths with the load resulting from adoption of new appliances like air conditioning, electric vehicles. That allows us to then perform a bottom-up characterization, such as shown in the chart on the right, where you can actually look at the various segments of load coming from, electric vehicles, residential, commercial AC, and sort of the base business as usual load, which is basically the rest of the users for electricity in the economy. So this bottom-up characterization model is not meant to be a forecast, but more meant to sort of be a scenario generation tool that allows us to sort of input a number of different assumptions around economic growth, technology assumptions, weather data, to then sort of look at how that manifests in terms of changes in load demand that then can be used for system planning efforts, both at the distribution level as well as at the bulk system level. So our subsequent sort of component of the analysis was very much similar to the framework that Kathy described, which is looking at capacity expansion models using the GenX electricity system model for the bulk system. In parallel, we also performed sort of a distribution and network planning analysis using a real options-based approach that can be particularly insightful and useful as we are thinking about the role for storage as non-wire alternatives to manage load growth in many urban distribution networks. So I'll start by describing some of our results for the evolution of the Indian power system and the role for storage, considering the combination of our bottom-up analysis on demand as well as supply-side analysis using our capacity expansion models. So here you're seeing a chart which we sort of define as a reference scenario where we don't have any carbon policy in place, and we're looking at sort of a baseline AC efficiency assumption along with sort of reference economic growth assumptions to then explore how the power system might evolve under this scenario. So what you see on the chart is the capacity deployment on the left and the generation mix on the right. And there are a few key observations here that are worth noting. So firstly, we see that renewables are really dominating new investments across the board, across the various investment periods that we're looking at. And to the extent that roughly half of total generation by 2030 could be provided by renewables under this scenario. However, as we start to see demand growing rapidly, we start to see increased utilization of both the existing coal, but also deployment of new coal capacity shown in the pink, that basically sort of results in the fact that emissions, when you sort of cumulatively look at them on an annual basis, tend to sort of have this non-monotonic trend where emissions decline, but then subsequently start to rise rapidly towards the end of the planning horizon evaluated here. So although the emissions intensity of the grid itself is falling compared to present levels because of the adoption of renewables, the overall emissions are increasing because of the substantial increase in electricity demand. So there's some interesting insights here that sort of point to the near-term potential for renewables in reducing emissions, but sort of thinking about these longer-term effects. The renewables growth rates that are being deployed here are sort of unprecedented compared to historical trends, and so it's definitely showing the possible potential of accelerating and deploying these levels of renewables. But it's worth keeping in mind that these are well above historical levels of deployment. So there's definitely that that factor to keep in mind. So if we then start to look at sort of honing in on the role for energy storage in particular, so we find that because India is very much a solar-dominated resource country in terms of renewables, and much of the new generation that's coming online is solar, and solar tends to dominate the overall generation mix. We see a lot of accompanying role for lithium-ion battery storage to sort of manage the mismatch in basically when solar generation peaks and when peak electricity demand occurs after sunset. And so that at 4 to 6 hours of duration basically sort of matches very well with lithium-ion storage's cost and performance attributes. And so you see a lot of lithium-ion storage in the brown, sort of under our reference lithium-ion storage cost scenario. And I should note that across all of these scenarios, we basically assumed natural gas as primarily being imported natural gas. So our assumptions around natural gas prices are relatively high. And so we don't see any significant role for natural gas in these grids as a result. And storage in combination with solar sort of are the primary mechanisms to drive and meet new demand. If we now start to look at what happens under scenarios with low lithium-ion storage costs, and these are costs inferred by NREL's annual technology baseline projections out to 2050, we start to see sort of the fact that low storage costs coupled with the accompanying ease of integrating additional solar on the grid means that virtually you can eliminate much of the new coal capacity that would be deployed in these systems. And so this is very encouraging because it sort of significantly changes the emissions picture, where emissions actually in 2050 are roughly approaching 50% or lower in emissions compared to sort of 2020 emissions. So we're starting to really sort of make a significant reduction in emissions while sort of meeting this significant increase in electricity demand during this time period. Now it's important to sort of make 2 points here. One is that that there is reason to believe that these low lithium-ion storage costs are not out of the realm of possibility. If we look at for 2 points, so one is we've had some conversations with some of the utilities who have been looking at quotes in this area that would be more in line with low lithium-ion storage cost projections rather than the reference case in the Indian context. And this is also supported by the fact that capital costs for solar in particular tend to be much lower for a number of different factors on a per kilowatt basis compared to the US context. And so there's definitely reason to believe that the low lithium-ion storage cost scenario that we modeled here is quite plausible. I'll also highlight that we did similar analysis with many of the emerging longer duration energy storage technologies that were mentioned in Kathy's presentation and in the previous hour. And we see that their availability also has similar effects as the low lithium-ion storage cost scenario. So either reductions in lithium-ion storage costs or the availability of these longer duration energy storage technologies could lead to effects that you're seeing that are quite similar, where substantial adoption of renewables could eliminate the need for new coal capacity. So that's the upside. The downside here is that we still have a pretty substantial base of coal generation in the system that basically remains virtually untouched given its relatively young age, and is not displaced by these cost drivers related to renewables and storage adoption. And so that in the absence of carbon policy or any other policy measures, really does not seem to be affected by these renewables adoption scenarios. So in the chapter, we discuss some additional policy scenarios which we think are potentially plausible, where that provides us a pathway basically for eliminating some of this existing coal capacity. But I won't get into it here just in the interest of time. One other major point to highlight here is that this storage capacity deployment represents a very large share of global energy storage capacity deployment, and in fact even exceeds BNEF's global projections. From this is a study that's now a few years old, but sort of highlights the very large market that India represents. So I mentioned at the beginning the impact of air conditioning. So we started to look at scenarios where we have higher AC efficiencies that overall basically reduces the peak demand, but also reduces annual consumption of electricity, as shown in this dispatch chart for a scenario with high AC efficiency versus the reference AC efficiency case over a summer period of 3 days. And so you can clearly see that the peaks have reduced, but also total consumption has declined. And so the overall story here is that yes, your annual electricity consumption declines, the peak declines, which means you need to deploy lesser new capacity, but because the demand profile structure changes from the sort of the peaky profile seen in the reference scenario, and is more akin to matching baseload generation, we tend to see an increase in emissions intensity on the whole, because coal generation looks more favorable in these scenarios, and you need lesser energy storage, but also lesser solar deployed as a percentage of total generation. So we sort of have this counterintuitive effect here, where focusing on demand side efficiency reduction measures, while ostensibly a good thing, without accompanying with policies to sort of manage emissions on the supply side, it could have these undesirable effects, possibly where emissions intensity could actually increase under some of these demand side measures. So storage also has a significant role to play in distribution networks, primarily in managing congestion on these distribution networks and deferring network upgrades that are premature to manage this increasing load growth. So in our analysis, we looked at 4 major Indian megacities and sort of did analysis of the feeders to understand the potential for energy storage deployment. And this dispatch chart is just an illustration of the use case that storage could have in these distribution networks, where the red line is sort of your line capacity, representing your substation capacity, and storage basically by shifting peak consumption or peak imports from the grid and reducing that peak allows you to basically defer these wire upgrades in an economical manner. So this is a pretty well documented sort of use case for storage that has been discussed in many different contexts. But I think that the important dimension here to focus on is that in emerging market contexts like India, where you have these very congested urban feeders that are more heavily loaded than, say, feeders in the US context, this use case looks more attractive. And this fact is then further compounded by the fact that because cost of capital is relatively high, wire upgrades tend to look more expensive than energy storage deployment when thinking about these peak shaving applications. Finally, I want to pivot briefly to just talk a little bit about the supply constraint region that I mentioned at the very beginning, looking at the use case of Nigeria. So for this application, we looked at the opportunity for storage to serve as part of mini grids that are connected to the grid to improve the reliability and also reduce the cost and emissions associated with power supply. So the one use case that we focused on was the use case of the Wuse market in Nigeria, which is shown in the picture here, which has roughly a peak demand of 1 megawatt. And because of the relatively poor quality of bulk grid supply, the use of diesel generators as backup for storing and maintaining refrigeration in these markets is quite prevalent. And so in our analysis, what we focused on was trying to sort of understand what is the opportunity for basically storage in combination with solar, as you can see from the many roofs there, that could make it a plausibility as part of this mini grid system. And so we looked at a number of different dimensions where we focused particularly on the conditionality of storage adoption as a function of the nature of the frequency and reliability of the bulk power supply, which is really sort of a key driver in this analysis. So in the case when you don't have any outages from the grid, or you have a pretty predictable nature of when grid supply might be available, you see a lot of storage being adopted in these scenarios to complement solar generation and to be able to shift the solar output to when peak consumption occurs, along with some continued use of diesel as part of backup supply. However, if you start to look at the impact of unpredictable and relatively long duration of grid outages as they are today, then lithium-ion storage, because just of its cost and performance attributes, becomes much less attractive as an option compared to diesel-based backup generation, even with some optimistic cost projections that we looked at in the study. So here, the sort of the displacement potential that you get from lithium-ion storage for these mini grid applications remains a less optimistic picture than what we might have imagined going into this analysis. So with that, I'll stop and then turn it over back to Rob to see what questions there might be. Thank you.
Yeah, Thank you both. There are many questions. Some of them very detailed, wondering about how we modeled certain things, and then there's some big question sorts of points as well. So let me start with Kathy. I said in my introductory remarks that EVs were not really directly a concern in the study. On the other hand, they represent a big load potentially. How are they handled in the models, say for the United States, the EV load? And are you using them to, as storage media, for example?
Mhm. Yeah, so for our demand scenarios, we're using the NREL electricity future study hourly demand, which is consistent with the electrified economy. So that includes EV load as well as electrification of space heating. But in the chapter in the section where we specifically look at demand flexibility, most of that is enabled by EV load. So that is a direct substitute for short duration energy storage like lithium ion. And I had talked about the substitution in install capacity, as well as how that looks like on an hourly operations basis. And we really see that it does reduces the need for lithium ion when it is available.
Okay. Oh, by the way, there are a couple of questions about the recording and presentations, and we will share them all probably within about 2 weeks after we've done a little bit of editing to remove my ums and does and make us all look smarter than sometimes we sometimes feel.
Rob, if I can just quickly add to that
Yeah.
response by just highlighting that we did not model vehicle to grid sort of applications, which are, a potential possibility, but given sort of some of the considerations regarding, the degradation of the EV battery, and sort of the remuneration for sort of the customer who owns the EV battery and some of those issues, we didn't really get into looking at that. So that's another piece of the EV grid integration that could have some impacts and increase the effects beyond what we're seeing here.
I think there was a general observation, I think, that several people made in different ways, that in part you're talking about a competition between electrochemical storage, or say mechanical storage, and natural gas as a peaking mechanism that could displace storage or eliminate the need for it if you didn't have to worry about emissions. And so the one question is, if you're just using natural gas for peaking, just to get those little areas when you don't have enough generating capacity or you don't have enough line capacity, don't you have to do CCS? And is CCS going to be viable for peaking applications? I guess that's a question for Derek or Kathy, whoever of you has a ready answer.
So I can jump in. So I think, yeah, that's definitely a technical challenge that I think current CCS technologies in their manifestation don't necessarily sort of fit that requirement in terms of flexible baseload generation. However, there are encouraging developments with respect to oxy-combustion based cycles that sort of have this capability to be rather flexible, but also do sort of high degree of CO2 capture. And I should just make a plug for the Department of Energy has an ARPA-E program focused very much on this flexible carbon capture technology, looking at an array of options in the space. So I think from the purposes of our modeling, we were rather optimistic about CCS's ability to be flexible in that way, while recovering its fixed costs, which is another aspect. But I think there's some room for sort of technology development in that space, which would actually increase the role that CCS plays in some of these scenarios relative to storage.
Kathy, feel free to add to
I
that.
think one part of your question was about if these peaking gas plants have very low capacity factors, whether or not it'll be viable. And within the settings of our model, every resource is made whole. So the costs of investments and operations are equal to the types of revenues that they can earn within this framework. That being said, we assumed a value of loss load of, I believe, $50,000 per megawatt hour. And given the current regulatory sentiments around these very high prices, this is definitely a question for future regulatory frameworks, some of which will be covered by tomorrow's session.
Yeah, thanks. I mean, just staying on the question of natural gas. I mean, you point out, Derek, again, in India, it's a sort of a competition between natural gas as well as residual coal generating capacity, especially newer coal generating capacity, which is going to tend to linger on the system for a long time, and storage. But I'm just, a couple of questions relate to the fact that we're going through a weather crisis here globally, in addition to a natural gas market crisis precipitated by Ukraine, or by the war in Ukraine. Ukraine didn't precipitate it. There are going to be crises like this over many, many years, and it can lead to volatility in gas pricing. I'm noticing spot prices for natural gas landed in India are anywhere between $26 a million BTUs and $56 a million BTUs, sometimes even north of that, way above your $11 so-called high gas price range. To what degree does uncertainty about gas prices and gas price volatility influence the trade-off between natural gas peakers and storage?
Yeah, so that's a great question, because when we started the study in 2018, we were getting the opposite question where, LNG spot prices were $3-4 or, in that range. So we were sort of in a gas glut situation. So, but I think, one of the things you see, the sensitivity of the scenario outcomes to gas prices is relatively muted compared to the sensitivity to some of the other assumptions in the model, like storage costs and renewables, just because, even with the so-called low $11 per MMBTU gas prices relative to present costs, you see very little adoption of of natural gas in these grids. So I think that's less of a challenge for India, but maybe more of a challenge for other regions where gas is a much larger share of the overall generation mix. So I think the bigger challenge in Indian context is there's just a significant quantity of existing coal capacity that, without any further action, kind of will stick around just because of the fact that they have a relatively young fleet.
Mm-hmm. I guess there's a retrofit opportunity there along the lines that Seiji was describing that must be enormous.
Exactly, yeah. So I think this is an area where this retrofits sort of have a potentially strong role to play, and we're sort of actively pursuing some projects in this space to sort of understand how these retrofit solutions can sort of be a practical solution going forward. One of the things about retrofits is that they may not always be the most cost-efficient strategy, but because of their sort of other dimensions related to socioeconomics, as well as reusing existing capacity that sort of reduces decommissioning costs, that could make them particularly attractive.
I guess for Kathy, you described briefly the assumptions about lithium-ion battery costs over the time of the study. Of course, it's extremely hard to forecast battery prices 30 years in advance. Say a little bit more about where those numbers come from, how confident or we think about the uncertainty in battery prices over time in the conclusions that you've drawn.
Sure.
Feel free either of you weigh in on that.
Yeah, our cost assumptions come from the NREL annual technology baseline ATB, and it's consistent with some of the estimates that we're seeing from the electrochemical study teams. That being said, there is a lot of uncertainties in the short term due to supply chain challenges, COVID, et cetera. But in the long term, we expect that some of these manufacturing capabilities will realize driving down the long-term cost of lithium-ion batteries. Derek, do you have anything to add to that?
Yeah, I guess I'll just complement that by saying on the longer duration energy storage technologies, the previous hour probably covered a lot of the sort of the basis for the cost estimation, and we're not necessarily forecasting costs here, but trying to sort of look at range of possible outcomes and how they drive system impacts when it comes to energy storage adoption and other effects. So there is quite a bit of uncertainty, but I think at least from in terms of the key factors that distinguish longer duration energy storage and lithium ion storage, the material costs sort of are pretty much in a different range. That sort of makes the case that there is quite a degree of confidence around those material costs being relatively lower compared to lithium ion, and hence they would have different roles to play in these grids.
Okay. Somebody made the observation that utilities have made major claims pushed by the regulators about their ability to decarbonize over the next couple of decades. Many of them have net zero, I would say not quite plans, but at least drawings that indicate how that's going to go. But there was some doubt among the questioners about the practicability of those net zero plans. I think Kathy's charts didn't exactly show the regions that we studied going to zero for no additional cost. Are we going to see an increase in the cost of electricity if we push for those 2040 or 2050 net zero outcomes?
Kathy, you want to take that? I mean, I'm happy to also
carry on.
Yeah, I think in terms of feasibility, we share that using today's commercially available technologies, we are able to make the system feasible. In terms of like at what cost, we assume that all these different dispatchable technologies are also available. The model just chooses the more cost-effective, which in this case are solar and wind technologies. So I think in terms of cost increases relative to today, I'm not sure what that amount would be, but relative to a scenario where there is no emission constraints, I think cost impacts are not as significant as people may think.
Yeah, and also I'll highlight that I think the cost of not doing anything versus the cost of sort of decarbonizing here is sort of the key question, right? And so there's if you impose an additional decarbonization constraint, which we don't have necessarily on grids across the US, we will see cost increases, but those are sort of dwarfed by the the costs of basically not addressing emissions reduction.
I think I understand that my video is having problems, so I've switched it off. So that's why I'm not. That's a picture. I think another question relates to the specifics, perhaps, of how Unix works. But an observation several people made was that you get an awful long way toward a fully decarbonized electrification system by getting to most of the carbon removed, but not all of the carbon removed. Say a little bit more about the cost of that additional piece and how you're thinking about the future electricity system vis-a-vis the rest of the economy. Can we find the equivalent emissions reductions elsewhere in the economy and accept a small amount of residual emissions from the power sector? Is there enough flexibility elsewhere in the economy to do that?
So one thing was, in our analysis, we sort of focused on the 5 gram case as a sort of a central decarbonization scenario because, the marginal cost of abatement from going to 5 to 0 sort of tends to exceed the costs we have seen in the literature for many negative emissions technologies. So in our mind, because we drew the system boundary to exclude those technologies in our analysis, and the fact that they are relatively nascent and quite uncertain, means that our analysis for a fully decarbonized power system is arguably more speculative, than what we would have hoped. So therefore, our sort of focus is very much on this 5 gram case, which, as you point out, gets us pretty much all the way there in terms of eliminating emissions. We're talking anywhere between, depending on the region, 99 to 99.7% emissions reduction.
Okay. Well, look, we're out of time. I mean, but tomorrow we're going to return to this in a different context, looking at getting to those very high VRE systems, and perhaps causing problems within the electricity market with all of this zero or near zero cost power coming onto the system. How will that work? What systems do we have to make, or rather changes we have to make in our regulatory system? So let me thank both our speakers, Kathy and Derek, and for unanswered questions, please refer to the study or reach out to us and we'll try to answer them. And we'll come back with the presentations and recordings shortly. Thank you all very much, and we'll see you tomorrow.